sometimes the basic comparison test is not good enough to solve our problems, and then the limit comparison test could come to the rescue. Let's take a look at an example and we'll see what I'm talking about. You see, we want to look at this series here, and okay, it looks similar to one that we saw before, but you see, we have that inequality there. So 1 over 2 to the n squared minus n is greater than 1 over 2 to the n squared. The problem is that this inequality is the wrong way, because you see, we know that the series on the right is convergent, but then we have that my candidate, like the one I want to study, is larger than a convergent series. But being larger than a convergent series doesn't say anything about the convergence, right? I mean, infinity would be larger than any number, so it's not telling you anything useful, really. Okay, but in a way, you expect this series to really behave like 1 over 2 to n squared. When n is very, very large, that is the one that dominates the behavior of my terms. So what the limit comparison test is going to do is precisely that, is that if I have a series and I think that I have another series that behaves pretty much the same way, it will give me a tool that will allow me to compare the two in a much more efficient way than the basic comparison test. So this doesn't help. We need to find something else, and that is the limit comparison test. And it tells me that if I have two sequences of positive terms, and I take a look at the limit as n approaches infinity of an over bn, and I see that the limit is L, and L is strictly between 0 and infinity. So the limit is a real number, but cannot be infinity, and L cannot be 0. Repeat. You look at the limit as n goes to infinity of an over bn, and that limit is a number that is not 0. Then we know that the series of the an's converges even only if the series of the bn's converges. So we know that both converge or both diverge. It cannot happen that one is convergent and the other one is divergent. That's why we're saying like they have pretty much the same behavior. So how can we study this? Well, we're going to assume that the series of the bn's converges, okay? And, well, the limit of an's over bn is equal to L. I'm going to use epsilon equals 1 in the definition of limit. And if I do that, I know that there exists an n naught such that the absolute value of an over bn minus L is less than 1 for all n greater than n naught. Okay? So if I have this, then what can I say? Well, if n is bigger than n naught, then I have that an over bn is the same as the absolute value of an over bn, because an and bn are positive. And now I'm going to add and subtract L, so I'm not doing anything yet. And now I'm going to use the triangle inequality to split this, because then you see I have one bit that I will control thanks to the limit, and the other one is just a number. It's L, I don't have problems with that one. Now I can bound the absolute value of an over bn minus L by 1. So this is less than 1 plus L. We have that an over bn is less than 1 plus L. Well, I can multiply by bn and we end up that an is less than 1 plus absolute value of L times bn for all n greater than n naught. Oh, but that's pretty good, because now you see all the terms an are less than a constant times bn after a certain point. So we can use our improved version of the basic comparison test to conclude that our series of an's is convergent. Now, the other direction, that if the series of an converges, then the series of bn converges, I'm going to leave it to you as an exercise. But hint, now you're going to want to use the limit of bn over an is equal to 1 over L. Why? Try to think about that and see how you can put all the pieces together.